2019 by Pavel Kovtun, Sasha Grozdanov, Petar Tadic, and myself. And by the way, let me just mention that Petar Tadic is currently looking for a postdoctoral position and is a very talented physicist, so please keep this in mind. And also the paper published in 2016 by Sasha, Nikos Kaplis, and myself. This is the audience, of course, who doesn't need any kind of motivation to study holography, but nonetheless, let me just show this one kind of propaganda type slide, which is supposed to emphasize that what we are doing is ultimately related, maybe indirectly, to various experimental programs and various theoretical advances of the last 2 decades. And I would like to emphasize the experimental side of this program. So we have a number of experiments on heavy ion collisions at RIC, which continue for 20 years already, and LHC, which continue for about 10 years. But also I would like to emphasize future collider experiments, which will be done in Germany at the Collider Fair, and in Dubna in Russia at the future collider NICA, heavy ion colliders, who will have various characteristics which would allow to study different regimes of quark gluon plasma. And I think we should be aware of the fact that these colliders are coming online, and that's an important thing for theorists to keep in mind. So various accounts of how this quark gluon plasma story is related to theoretical advances are published. In particular, there is this book by Romashke and Romashke, right? And also various reviews, such as a review by Krishna and collaborators on heavy ion collisions. And I will not say more about this. So we all know that there is one characteristic which unites these experimental advances, and the characteristics is that they're dealing with strongly interacting systems in or out of equilibrium, and these systems may be relativistic or not, but strong interaction is one theme which unites them all. And of course, there is gauge string duality, which is a common advance to a tool to study strongly interacting quantum systems of a particular class. But that's good enough for us. So I will focus in this talk on a rather simple question. So we all know that hydrodynamics is an effective theory valid at long distances and long times and large distances. But there is a question of what are these large distances and long times, and what actually sets the limits of hydrodynamics. I think this question is theoretically quite interesting. And in particular, within this question, we can ask what happens to the dispersion relations of hydrodynamic modes, the gapless modes, such as the shear diffusion mode with the dispersion relation shown here, and the sound mode, which has a dispersion relation which starts with linear Q. So these are modes which are given by infinite series in spatial momentum, powers of spatial momentum squared. And one may naturally ask a question whether these series converge, and if so, what determines the radii of convergence. So does the effective theory somehow knows the limits, right? So one very primitive example is the dispersion relation for a relativistic particle. So imagine that we knew nothing about the special theory of relativity, and we didn't know that dispersion relation would look like square root of p squared plus m squared, right? So I subtracted m here just to start with p, right, p squared. And suppose we didn't know that, right? And in some very painful investigation, we would start learning the coefficients of the small p expansion, right? So the first, the second, the third, and so on. And then somebody would discover that the series actually diverges at a certain value of p. Then this divergence would somehow convey to us that this description fails at a given value of p. And this given value of p is, of course, set by the non-analyticity of the actual expression, which is located at complex value of P. So in principle, you would never be able just to detect it by conventional means, so to speak, from the series, because the function looks fine at P equal to M, but nonetheless there is this divergence. So so this is the same question one can ask about the hydrodynamic series. If there is a certain value of momentum which sets the radii of convergence for the dispersion relation in hydrodynamics in general, in weak coupling and kinetic theory and so on and so forth. So thanks to holographic duality, these questions can be investigated quantitatively and analytically, at least for some quantum field theories. So just to give you one motivational slide about the interpolation between weak and strong coupling in general, right? So I keep stressing this, that in one and the same theory, for example, in n=4 superrank-Mills, in principle, we should be able to, at least qualitatively, to understand how things change from weak coupling to strong coupling. And in particular theories, in particular questions which are related to not only to thermodynamics, but to states away from equilibrium, can be in principle investigated in this way. So here is an old and beautiful example from Eriksson, Simonov, and Zaremba, which is 20 years old, right? And one of the very rare examples of an exact answer in such a situation, right? An expectation value of a circular Wilson loop in n=4 superrank-Mills in 4 dimensions in the limit of infinite number of colors, but exactly in lambda in Hopf coupling, right? So the expression is given by modified Bessel function, which happily can be evaluated at weak coupling perturbatively, right, and gives this result, and then non-perturbatively is in the symptotic series at strong coupling, and it coincides with holographic calculation of strong coupling and perturbative calculation at weak coupling. So sadly enough, we don't have such exact results at finite temperature, right? So even the free energy, we don't have a full interpolating function at infinite MC, not to mention transport and other stories. So this is complicated. Then another motivational slide is this unreasonable effectiveness of hydrodynamics, which people like to talk about, right? So let me just say that if we have by holographic means, we have an option to look at the full nonlinear evolution of a given system, maybe a rather exotic system. And this full nonlinear evolution tells us how the components of the energy momentum tensor, for example, T naught component, which in equilibrium will be the energy density of the system, evolves as a function of time. And this has been done in a number of impressive papers, in particular the one by Chesler and Yatha and subsequent work. And it shows that in some situations, at least, hydrodynamics works pretty well, in fact, unreasonably well, in the situations when we don't have local thermodynamic equilibrium. So here you can see that the pressure gradients are still quite large, but hydrodynamics, which is denoted by this dashed line, coincides pretty well with the so-called exact evolution extracted by this holographic duality. Right. So it's interesting to understand why this is so and what sets the bounds for this effectiveness. So I will not discuss a number of relevant issues in this talk. Nonetheless, these issues are very interesting, and for those who are interested, I provided some references here. So there is this whole story about the causality problems in relativistic hydro and resolution of these problems, which has been achieved in a rather impressive series of works by Kofton collaborators and then by Naronian collaborators. And all of this is an ongoing, in some sense, ongoing work, as you can see from the dates of publications. The second part is the convergence, divergence, resurgence, and all sorts of variations of this word in the position space. So I will not talk about position space. This is a rather subtle issue, right? So you can have convergence in the momentum space, and then you may ask what happens in the position space, right? And as we know, Michal Heller and many collaborators of Michal and various combinations, which at least all the papers on the subject. So they investigated, for example, in Bjorken flows, the issues of these divergences, the asymptotic series, the resummations, and so on. So this is a wonderful story, which I will not touch. right? And that is a separate piece, although it is related to, in principle, to what I'm going to discuss. And then finally, a related piece to this is the relation to the singularity theorems in general relativity and stability analysis. So I just give one reference to this recent paper by the Fermas and company, where relatively recent, where they discuss the stability of the Schwarzschild black holes, and this is related to this convergence in position space, because it's all related to the class of functions which you deal with in the position space and so on. So functional analysis. But again, so I won't touch this. All right. So let's just focus on one simple thing, right? So what limits the convergence of these dispersion relations? Now, fundamental degrees of freedom in Hydra, densities of conserved charges, and equations of motion and conservation laws plus constitutive relations. All right. Here we don't touch another issue. It's the issue of the so-called long-time tails or non-analyticities, which in holographic quantities appear at finite NC. Right. So for us, NC is infinite, and we don't deal with these issues in real life. Of course, these issues are present, and in some sense, they strictly speaking, they will invalidate everything I'm going to say. Right? But we can happily separate, having this parameter NC, we can separate these two issues one from another, right? So for us, Hydra will be constitutive relation. So this will be Taylor expansion in gradient expansion without any non-analyticities in frequency, for example, which is related to these long-time tails. Okay. So the typical expansion for constitutive relation for relativistic T mu looks like this, right? It enters with a number of transport coefficients, which are defined by microscopic theory. So in conformal case, to first order, we only have shear viscosity. Then to second order, there are 5 more coefficients. And then you can go on and investigate more and more terms in these expansions. And in fact, I think only third order expansion has been investigated so far by Grozanov and Kaplis, and that some people may say it's not even fully complete. But nonetheless, we know that the number of transport coefficients will grow with the number of terms. And this growth is, we probably don't know how fast they're growing. This number is growing, but it's clear that the number increases fairly fast, right? So there are 20 relevant structures in the conformal case, tensor structures, and 68 in non-conformal one for third order Hydra, and possibly far more in the fourth and so on. But yes, and from that you can derive the physical dispersion relation, right? For example, for sound, right? So here at the bottom we have the dispersion relation for the sound wave to third order Hydra. Right, so it contains the usual beginning, right, the linear in momentum, then the k squared term, this is all known, and then there is k cube, and then k to the fourth. And these guys, they contain the transport coefficients, which come already from the third order hydrodynamics. All right, so before sort of coming to the main topic of this discussion, let me just mention our precursors. So obviously every work has precursors. So in our case, there was a series of works by Michel Lublinsky, which investigated the all order Hydra resummations, and that was quite important for us to understand what they were doing for a number of years. And then there was a very interesting paper by Ben Vivers in 2018, where a finite density, so it was Reisner-Nordstrom ADS4 black brane background, and we were in some sense motivated by that paper to understand why N=4 superrand mills with zero chemical potential wouldn't follow the pattern that was investigated in Ben's paper. All right, so now finally come to the actual substance of the discussion. So we consider relativistic Hydra to all orders. Right? So what do we have? We have expectation value of T mu. Expectation value of T mu is a function which has an equilibrium value, and we can consider, so if we settled with some equilibrium configuration, right, and we understand very well what this equilibrium means, then we can discuss fluctuations, small fluctuations around this equilibrium state. right? So for example, the typical, so we will be talking about the simplest possible situation in which our equilibrium state is homogeneous and isotropic, right? So everything will be extremely simple. So in that case, equilibrium T mu will have this form of diagonal epsilon PPP, where P is the pressure, epsilon is energy density. And what we want to understand is the fluctuation of this T mu on this equilibrium state. Now, fundamental degrees of freedom are densities of conserved charges, which means T naught naught, right, in our language, and then T naught I, right? So there are four of them, four variables. So all other components should be expressed through them and the derivatives via constitutive relation. Now, to linear order in fluctuations and in Fourier space, one can write down the expression for constitutive relation for all other components, delta T ij, via our fluctuations of the densities of conserved charges, just looking at the symmetries of our problem, right? We know that there is isotropy, right, and things like that, right? So just by looking at the tensor structure of the objects, we can write down the generic formula, which again, so this does not imply any gradient expansion, right? This is completely generic. The only requirement is that we are linear in fluctuations. So we have these tensor structures, right? And then in front of them, there are functions A, B, C, D, and E. And these functions will depend on omega and Q squared. Q squared because the system is isotropic, so it cannot depend on components of momentum alone. It depends on the full length of the momentum vector, right? So this is, in some sense, I mean, everything else follows from here, right? So we have this generic formula, right? And then if we want, we can expand this expression in powers of momentum Q, right? Around zero. And this will give us derivative expansion. So for example, to first order in hydrodynamic gradient expansion, we just expand this A, B, C, and D, right, to first order gradients, and we will get expression for delta Tij in the following form, right, where you can easily identify what is what, right, so by comparing these two formulas. But this reminds us of the standard relativistic hydro expression constitutive relation for delta Tij, right, to first order in hydro, But again, so we don't want to do it, right? We don't want to work with a full expansion without assuming this gradient series. So then fine, so we have constitutive relation and we have equation of motion, which is conservation of T mu. And then we combine the formula above, the constitutive relation, with the conservation equation, d mu T mu equal to 0, and we get a 4x4 matrix equation for the fluctuations of our fundamental degrees of freedom, delta T naught naught and delta T naught I. Right, this matrix can be easily computed, and obviously to get a non-trivial solution, we must have a determinant of this matrix being equal to 0, right? So if you have a relativistic homogeneous and isotropic neutral fluid in d+1 dimensions, then computing this matrix will give you this determinant, right? Computing this determinant will give you the following expression. So this expression naturally factorizes. It has one piece to power d minus 1, and then there is a second piece which is quadratic in omega, and this whole thing is supposed to be equal to 0, right? These functions, gamma, eta, gamma, s, and h, are related to the original functions a, b, c, d, and e in the constitutive relations, and of course they are not known. So for a given microscopic theory, these functions must be computed by microscopic means, right? So, but we don't need this. We just have this general analysis of how the series will look like. So fine. So we will call this determinant, right? This let's call it P now. We call it a spectral curve, right? It's a term unfortunately used in many other contexts, but let's just do it, right? So we have two hydrodynamic spectral curves. One is the shear curve here, F shear equal to this thing equal to 0, and then there is a sound curve, right? So then we treat them as complex curves, and this is a crucial step, right? So we have these two curves which would give us dispersion relation in principle, but in order to understand the analytic properties of these dispersion relation of this series, we have to treat them as curves in complex space. So our omega and q squared, not q squared, are promoted two complex variables. So this is a complex curve in the space C2. All right. Okay. So
sorry.
Yeah.
Hi, Andrei. Can I ask a question?
Of course.
So here you have this shear channel and this gamma eta. Of course, the lowest order in omega eta will be a constant, and that's the diffusion kernel, right?
Yeah.
Now, of course, having a diffusion kernel is sort of bad with causality, right? How does this get repaired here?
It doesn't. So we are not. So this is the causality issues, right? So is in some sense is a separate story, right? So we have to. So we know that So relativistic hydra will be a causal, right? And kind of naively, let's say naively a causal. And it's not a physical problem because this causality comes at the values which are not compatible with the regime of applicability of hydra, right? But from a point of view of the present, so basically what I want to say is the following: whatever you write as a constitutive relation, right, will enter this gamma. So this gamma is not secret. If you have a scheme like Kofton, for example, right? If you have a scheme in which your constitutive relation will be the most general constitutive relation so I don't want to enter this issue of frames, right? So in a given frame, so you will get the appropriate gamma, right? So the statement is that physical results should not depend, of course, on this choice of frame.
No, but what confuses me is that you have not assumed a derivative expansion here, and
that's right. Yes,
right.
Yes.
So usually we say, well, this acausal behavior is outside the validity of the derivative expansion, but this seems to be an exact statement here. The only thing.
Yes.
Confusing.
Yeah. So okay. So far we haven't assumed anything except the fact that we have an equilibrium with given symmetries and small fluctuations on top of this equilibrium, right? Now, and linearity, right? So our fluctuations are linear. We do not assume a specific gradient expansion, which can be different as we just discussed, right? So it can be chosen in different.
Even here, I mean, if you do that, you see, my point is presumably you assume the gamma eta to be analytic in omega and q squared.
Yeah, that's a very subtle. Yes, that's right.
So when you do that, you know, it's very hard to get rid of how do you get rid of the causality? I mean, because as you said, you assumed equilibrium and you assumed linearity, right?
Yes.
And that's all you assume.
Yeah. So
somehow, usually I assume you also assume derivative expansion, and then things go wrong, and but here you don't even assume this. So what is going wrong?
You can sort of I think you can separate the issues of gradient expansion completely, right? So think of them as poles in the correlation functions, 2-point functions in a relativistic QFT, right? So we have relativistic QFT, which is of course is causal, everything is fine, right? So right. And it has a number of poles, right? These poles will have dispersion relation, right? So that's right. And we are investigating convergence of these dispersion relations, right? So by any means available, right? So that does not. It's a physical result. I mean, the existence of these poles and the properties of the convergence of the appropriate series does not depend on how we formulate relativistic hydra, right? So this is a property of QFT.
Yeah. Okay. Right. I don't want to go on.
Yeah. Okay. We can. Yeah. Sorry. We can continue this discussion maybe offline. But yes, I mean the most important thing here is of course a certain assumption about analyticity of the coefficients of these spectral curves, which I will come to in a second. So at any finite order of the gradient expansion, this spectral curve is a polynomial in omega and q squared. And moreover, one thing, again, I don't want to go into this, but in principle, you can use equations of hydrodynamics to shift various powers of omega and q from one order of your expansion to another, as often is done as field redefinitions, right? So you can use equations of motion to do that. But again, so here I don't want to enter this discussion of the order by order kind of derivative expansion in hydrodynamic contents, right? So suppose we have to this curve to all orders in omega and q, as we do in holography, right? Because holography provides us this thing to all orders in principle, right? So what can we say about these complex curves in principle, right? So what can be done with them, right? So complex curves are very interesting objects, and I don't know much about them, but there is one property which will be of interest to us. We would like to express, so given a complex curve f of x and y equal to 0, where x and y are complex variables, we want to express y as a function of x, right? We want to solve this thing. So, for example, we have this complex curve, which is quintic, right? So y to the fifth and so on equal to 0. And we want to solve this for y as a function of x. So how to do this in general, right? So there is a theory, there is a machinery of how to do this. So it depends on around which point we want to expand, right? So there are regular points. Regular points are defined by the statement that the curve itself at this point is equal to 0, but its derivative with respect to y, because we want to solve y as a function of x, not x as a function of y, is not equal to 0. And then the implicit function theorem guarantees that around this point you have a convergent Taylor expansion of the standard form y as a function of x minus x star to power n and so on. Now, there are also critical points. The critical points are such that the curve itself, given by equation f is equal to 0, but also the derivatives with respect to this variable y to order p are equal to 0. To order p minus 1 is equal to 0, and derivative of order p is not equal to 0. So for us, the most interesting case will be when p is equal to 1, right? So the first derivative vanishes, but the second doesn't. But in principle, this can be continued to any order, all right? Then in 19th century, people explained to us, right, how to write down the analog of convergent Taylor series around such points, and this was done by Puiseux. And Puiseux explained that the series will look like this, so it will be series in fractional powers, and the fractional powers can be determined from the explicit form of the complex curve. There is a machinery of how to do this, which I will not elaborate on. It involves the so-called Newton triangle and all this wonderful mathematics, which again, so I don't want to go into these details, but in principle, this is an algorithm which is well known for people who work with complex curves. But for us, it's important that this algorithm exists and can be applied to the hydrodynamic curves, which we just discussed, right? So here is one digression, which I cannot resist but pointing out. These issues are quite remarkably showing in such old problems as a motion of planets, Kepler problem, Kepler's law, right? You can notice that Kepler's third law contains non-analyticity, right? The periods are proportional to the fractional power of the major semi-axis, 3/2. And this is not an accident. So there is a story behind this. But you can look at this whole story in the following way. So take the motion of a planet parameterized by parameter psi. So this is a parametric form of the motion in polar coordinates, which you can take from any textbook on classical mechanics. And this parameter psi, which is known as eccentric anomaly, it determines the position of planets. So it's enough to know psi, and then you substitute, and then there are formulas which tell you where the planet is on a sky. Right? So that's very simple. Now, this equation, t equal to right-hand side, is known as the Kepler equation. I rewrote it in a slightly different notation, but it's the same equation. So t, or normalized tau, minus psi plus eccentricity times sine psi is equal to 0. This equation was solved by Lagrange in 1771 in the form of a series. Lagrange apparently was not concerned about the convergence of the series, but Laplace was. So in 1823, he demonstrated that the series is actually divergent if eccentricity exceeds a certain critical value, which is known as the Laplace constant. So this is something which points 0.662743. Right? And as we pointed out by Arnold, so this is a long quotation from Arnold, but I think it's quite remarkable that this equation, the Kepler's equation, plays an important role in the history of mathematics. From the time of Newton, the solution has been sought in the form of a series in powers of eccentricity. The series converges when E is less than some number. Investigation of the origin of this mysterious constant led Cauchy to the creation of complex analysis. Right? So even though in Arnold with his flamboyant style, it's difficult to kind of ignore such statements. And in fact, when we wrote this paper, I had to actually read a number of original articles, very conveniently put online by the French Academy of Sciences, I believe, right? So all of this is digitized, and you can actually read these 19th century journals, right? And it's really remarkable how, yeah. Anyways, so the point is that what determines this convergence, right, of the series? Well, you can look at the critical points of the Kepler curve, right? The curve is given by this equation, f is equal to 0, right? Then you compute the derivative with respect to psi, right? You have to solve psi as a function of E, right? You have two complex parameters, psi is complex and eccentricity is complex. And then you solve these two equations simultaneously and look at the complex plane of eccentricity. And you discover that there are critical points. There are many of them, but the radius of convergence is determined by the one which is closest to the origin, right? Because you're expanding around E equals 0. And the closest to the origin critical point is exactly this Laplace mysterious constant, except that the critical point is actually located on the imaginary axis, right? So this is a rather cute example which shows how to work with the with this machinery in very simple and familiar situations. So let's apply this to our hydra, right? We have these spectral curves, the shear and the sound one, and we just apply this piezo machinery to this, right? And the piezo machinery, which again, I admit there is this Newton triangle and so on, you can read in our paper all these details. It just tells us several things. So it tells us that there will be two hydro series. One of them is for the shear mode, and this hydro series will come in powers of q squared, because this piezo machinery determines exactly which power is the power of expansion, and it tells us something about the coefficients as well. So the moral of the story that so only from the spectral curve you can say that the series must have this form, and there's nothing else. There are no some extra powers of q squared, some non-analytic powers, and so on. So this is how it should be. And then for the sound mode, the series must have this form given here, right, where Cn and An are real coefficients. Now, the second statement is that the abstraction to the convergence of this series is the critical point of the spectral curve. So if 0 is not a critical point, then the next one, just like in the Kepler problem, the abstraction to the convergence of the series will be the next to, with respect to distance to the origin, the next critical point of the spectral curve. And you don't have to expand the series, you don't have to analyze the coefficients of the series, you just have to look at the spectral curve and analyze the spectral curve, namely the derivative, the first derivative of the spectral curve equal to 0, and this equation tells you the location of all critical points, and the one which is the abstraction, right? So let's do precisely that. So this is one slide. So now I replace all the slides introducing ADS CFT by the one which was stolen from this wonderful talk by Shamit Khashrow in 2019. So this is a holographic duality, and I won't say anything else about that, right? So that's so for people who do holography, right? So it's all known, right? So how we extract spectral curves in holography? Well, we solve our equations of motion. This can be a rather complicated system of coupled equations, of course, right? So things are not as simple as on this slide, but we all know in the last 20 years how to work with these things, even in rather complicated situations. And the moral of the story is that the correlators, the retarded correlators, are proportional to the ratio of coefficients B and A in the solutions of these equations, right? So A equal to 0 gives us a spectrum of quasinormal modes, and it also gives us the spectral curve of our problem, right? So this is denominator of our correlation function GR. So all we need to do is to set A to 0, right? Having the equation of differential equation, and also set the derivative of A to 0 and compute the appropriate critical points of this curve. So obviously this is easy to say, right? So in most cases you have to do it numerically, in fact, almost in all cases. But nonetheless, it's a machinery, and we can apply this machinery to the cases which we know, right, in holographic situations.
Sorry, Andrei,
Yeah.
I have another question.
Yeah.
Before, if I understood this correctly, there was one spectral curve for the shear channel and a different one for the sound channel.
Yeah.
Now there's one spectral curve, because I know when you do this, right?
No, sorry, this was just an illustration.
Okay,
I mean,
okay.
Yeah, sorry. No, of course, yeah, for each channel, there is its own spectral curve. And things become even more interesting, shall we say, if we have a coupled system, as you know very well, right? I mean, you wrote one of these papers dealing with mixed fields, right? So but basically it's all. I mean, in that case, the spectral curve will be the appropriate determinant, right? So the determinant, as you showed many years ago.
Sorry.
Yeah, right. So this is just an illustration with one equation. So okay, so let's look at n equals 4 super-Mills, right? The spectrum is known for many years, and we look at the singularities of retarded Green's function in a complex frequency plane. So here for the shear channel, right, where we know that there is a hydropole sitting on the imaginary axis. Well, we know the dispersion relation, which is an infinite series, and we want to understand the radius of convergence of this series, right? So this is what Ben Vivers was looking at in his paper in 2018, except that when you have finite density, then things in some sense are morally simpler, because there is a mode on the imaginary axis which collides with this pole and so on, so you can see this mode. Now in n equals 4 super-Mills, if you look for real momentum q squared at the spectrum, right, and change your q squared as you like, these guys don't collide, right? Nothing happens to them. So they can move with q right around, and we know how they move, but they don't collide. These levels don't cross, right? So one may think maybe radius of convergence is infinite simply, right? So that's one possibility. So I have to explain maybe that why the collision is related to this notion of critical point, right? So recall the condition for a critical point of the curve, right? That's the function itself of the curve equal to 0, and derivative of the function, or let's say some number of derivatives, are equal to 0. So for example, so this means that this is actually a level crossing condition from quantum mechanics, right? Because what does it mean that the derivative with respect to y, for example, is equal to 0? It means that in one of the roots of the curve, it looks like y minus some function y star to power p. So for example, if I don't know, if you have a first order collision, then you would have sorry, this should be right. So it should be squared, right? So then the curve itself, right? The derivative with respect to y, right? If this p is equal to 2, right? Then the derivative with respect to y will have this thing vanishing as well, right? So then it means that the two branches, right? The two branches of the spectral curve, if this is a polynomial and you factorize it as a polynomial, the two branches must be equal to each other at a critical point, right? So we expect omega 1 at some value of q squared be equal to omega 2 at the same value of q squared, right? So this is a condition of critical point. So this is so-called quasinormal level crossing. And the kind of a surprise, if you want, is that it doesn't happen. Let's say it doesn't happen all the time at real q. It can happen at complex q. That's all, right? So basically, this is all we have to accept, right? So because at real Q, the dispersion relation is such that these lines don't cross, right? So there is no level crossing at real Q, but at complex Q there is, right? So you take what you do, you take Q squared as a complex variable, right, of a given magnitude, and then you vary the phase e to the I phi, and you vary the phase. So what happens in the complex frequency plane? For example, this is an example. This is a shared channel with magnitude of Q squared equal to 1, and you change the phase. So this is your original spectrum with the shear pole sitting on the imaginary axis, and then this Christmas tree guy sitting to the right and to the left, right? These are solid dots. And then you vary the phase, and all of them start moving. They start moving counterclockwise, and then after 2 pi, right, they come back to the original position. So these are the lines, but they can cross, right? So at small value of magnitude of Q squared, they don't, right? It's shown as this picture. But if you increase the magnitude of Q squared, eventually they start crossing. And they start crossing, like this is shown in this figure here, right? So these are red stars. They show, right? So these Christmas tree modes, they follow this kind of complicated Ptolemy trajectories, right? So they have this retrograde motion, is rather curious. But the point is that at some point, they touch the trajectory of the shear mode pole. And if you keep increasing Q squared, they form a happy family of 3, right? So on this Q squared equal to 2.23, you see that now the poles which were isolated on the original picture, right? The shear diffusion pole and the 2 Christmas tree poles. Now they become 1 in a sense, right? So they interchange their positions under monodromy. Then the phase goes from 0 to pi, right? So the shear mode becomes the Christmas tree pole mode, and Christmas tree pole comes to a different position on Christmas tree, and this left guy comes to become the pole on the imaginary axis. So this happens.
Can I ask a question, please?
Sure. Yeah.
So, just to point out, I think that, even at finite density, these collisions happen at complex Q.
Yes, at Q squared. Yes, at Q squared.
And even also complex Q squared.
At Q squared equal to negative, so it.
So at complex Q squared in general. So if you look at Christiana.
Yeah. I will mention this later. Yes. But so and Q squared is equal to so we will come back to the complex Q squared plane, and then I will come on.
Okay, thanks.
Okay. Right. So okay. So this is this is a story, and the same happens in the sound channel, right? So we can look again at these modes. They do various complicated things, and then you can do so. Just to emphasize that this is nothing more than the quantum mechanical level crossing. What we can do is to pick a phase, right? So pick a given phase when this crossing or this collision occurs, and plot our spectra just as we did on one of the previous slides right here. So this is the dispersion relation of omega, imaginary and real parts, as a function of real Q, right, from the old papers. And we can do exactly the same, but now for complex Q squared at a fixed phase. And then we see that there are level crossings, and there are many of them. So this is happening at a specific value of Q squared, right? And then many times later. All right. As Ben, so we can look at this at these singularities in the complex Q squared plane as well, right? So these are the singularities, as Puiseux tells us, right? They appear in the form of branch points of various degrees, and one can determine actually the degree of the branch point from the complex curve. Now, the situation which Ben describes corresponds to the branch point being located on the imaginary, on the negative real axis of Q squared. But what I would like to emphasize is that the one which which gives an abstraction to convergence, is the closest to the origin, right? So there are many of them in the plane, and moreover, they can move as a function of some parameter if we have some additional parameter like mu over t, right, in a non-zero density situation, or coupling constant, or things like that, right? So these guys will move in a complex plane as a function of this parameter, and the one who comes closer to the origin determines the radius of convergence, right? So that's this is what happens for n equals 4 super Mills, these two pictures, but again, as already mentioned by Ben, right, at finite density, you can have a different and even more complicated situation, as was recently investigated in these two papers, in particular by Jensen and Pantelidou, because these guys missed a bit. So it's an interesting story on its own. But yeah, so kind of morally speaking, this is the same situation in the complex Q-squared. Okay, so
Andrei, I think Hesam has a question.
Yeah.
Sorry to interrupt you.
Sure.
I have maybe a stupid question. When the joining of the modes happening in complex K, I was wondering if it's always in an order that first the hydro mode join to the lowest non-hydro mode, and then they join to the other ones, or it can be like chaos.
Yeah. Yes. So the answer is no, and this has been looked at. In fact, you can look at the scalar channel of the same fluctuations, right, where you don't have hydro modes at all, right? So you can take a minimally coupled massless scalar, right, and this grounds, right, and look at the critical points. And there you will see that there are no hydro modes to begin with, right? But nonetheless, this phenomena, of course, is happening, right? And it is happening. Under, roughly speaking, in the same spirit as was described, right? Although there are some peculiarities which I can talk about later with you.
But again, in that case, it's like the lowest modes join to each other first, and then the higher modes.
Yes. The modes with lowest magnitude, so on top of the complex plane, so to speak, right? So then I start doing this, and then it proliferates below, right? So that's
okay. Yeah. Thank you.
Yeah. Okay. So I'm close to the end, actually. This is a rather simple message, if you want, right? So what was done? So this machinery was applied to n equals 4 super Mills in the holographic limit, right, in the limit of infinite n c, and because obviously finite n c, as I mentioned in the beginning, right, will ruin the whole story because it will introduce non-analyticities in the hydro to begin with, right? So that actually is an interesting story itself, but in the infinite NC limit and infinite lambda, Hopf coupling lambda, the statement is that n equals 4 super Mills has a finite radius of convergence for the shear mode and for the sound mode. And these radii are given by these expressions here. So these are, roughly speaking, Matsubara frequencies times some number whose origin is perhaps mysterious, but they are of order 1, so both of them, right? And that's a statement. So this is as much as we know, right? So the one natural question to ask is what happens to these radii of convergence if you change coupling, right? So you have this infinite coupling result, and you may ask a question: what happens in kinetic theory? What happens? You can ask the same question, right? So you have dispersion relation. So what is the radius of convergence in weakly coupled gas, right? And all these things, right? And then the question of interpolating between the two limits. So this question may not be entirely trivial. We thought at the time that it's sort of straightforward, but now, so one can do a crude estimate. The crude estimate is the following. So take we have a full spectral curve, right? Which is which has to be extracted from let's say, from holographic calculations. But we can also write down the same spectral curve based on the hydro expansion. It's a crude approximation because we are limited to first order expansion, for example. But nonetheless, why not, right? So if we do this, and we know all the ingredients in this expansion for all coupling corrections of these hydro ingredients. So for example, correction to the shear viscosity entropy density was computed many years ago. So we can combine these expansions, and at the expense of being very crude, right, of kind of throwing away all the tail, we get the following, right? So the crude estimate gives us for its sound radius of convergence for the sound mode will decrease from strong coupling to weak coupling, right? In the following manner. So it will go like 1 minus some number divided by hot coupling to power 3/2, as all of them go, right? So the minus sign here is kind of suggestive, but let me say that so it appears that the radius of convergence is smaller to weaker coupling, and hydrodynamics in strongly interacting system seems to be therefore more robust, right? But before making all these wonderful statements that yes, of course, we expected this all along, right? So all the body of evidence tells us that it must be so that hydro works so well exactly because it's a strongly coupled systems, right? I would like to have a word of caution, because actually this may be a little bit premature. I mean, this statement about this minus, I mean, it is correct within these crude approximations, but if we do this honestly, as we are trying to do with Peter and Sasha at the moment, then things are actually slightly more complicated. And at the moment, we are not ready to say that yes, this is really true. All right. So let me. I think we spent too much time on various technical things. So I probably finish here. Because it's also a second part, but I think it will be responsible to start it. The second part was about the finite coupling, but let me not say about this and just finish here. And if there are any questions, then I'm happy to answer.
Thank you very much, Andrei. That was very good overview of the work done on this. Do we have questions?
Yeah, hi, Andrei. So thanks for the talk. This was very, very interesting. And I would like to ask one question. You know, the whole story here reminds me a lot to what in physics we did in the old times with respect to Seiberg-Witten theory, where you also look to how lines in the complex plane cross and give a physical interpretation to this singular point. So one of the things you can do there is you have the spectral curves, and you can define some moduli space, and there's some torus, you know, or more general abelian variety, and there's a theory which is this Picard-Lefschetz theory, which allows you to write some sort of differential equations on this moduli space, and then you see the singularities you see as regular singular points of these differential equations. Is there a similar story here? This would presumably be differential equations with very, very high order of derivatives, right?
Yes. So the honest answer is I don't know. I tried to. I mean, this Picard-Lefschetz thing is rather suggestive, kind of in applications to these matters. I'm not sure I have anything of substance to say, but it's only because my knowledge of these matters is unfortunately extremely limited. I mean, from mathematical point of view. I know, so there is one sort of rather simple, but to me it's a painful question, which in fact maybe somebody in the audience can immediately resolve. You see, in this language, the very existence of the hydra, because we can ask a question when, so for a given theory, so for a given Lagrangian, when does a Hydra regime exist at all, right? Just a priori, right? Can you say that there is a regime, right? Which is related to the fact that to the question whether the radius of convergence for, let's say, Hydra modes is non-zero at all, right? So is it non-zero? And this is in holographic context. It's simply a statement of whether the dependence on the so whether the solution, because the spectral curve ultimately is the solution of the ODE at a given point, at a fixed point, at the boundary, right? There is nothing else, and it's function of parameters. Now, the dependence on parameters is known from the equation, and usually it is smooth, right? So usually we control this. So suppose we know that the dependence is analytic on the parameters. Can we say something about analyticity of a value of the solution of ODE at 0, for example, immediately from that? If we can, then it's a statement that holography knows that, for example, a theory such and such has a Hydra regime, right? We have a non-zero, because if a function is analytic, it is analytic in some vicinity, right? It cannot be analytic, so it has non-zero radius of convergence of some kind, right? It may be very small, but nonetheless it's non-zero, right? And yeah, so this is related to basically this simple statement in the theory of ordinary differential equations. And to my shame, I really cannot have an answer, because that would be a proof of existence of the Hydra approximation in a given theory with gravity dual, right? So plain and simple. That in principle would be an interesting statement, because a priori it's not guaranteed that a given theory has a Hydra regime.
Okay, thank you. If I just a very quick question for related to that.
Matthias is a boss.
Right? So far, the spectral curves here, they are codimension 1 in a complex two-dimensional space, right? And so if you have two modes, basically there are two lines and they have to cross somewhere, right? Now, and I think these points which you showed, these were precisely such crossing points, right? Where two modes collide. But there are these higher critical points where modes like come together and touch. And so do they have some specific physical interpretation? Have you encountered anything like this?
Yeah, that's again, it's a question which I'm afraid I cannot fully answer. So in our paper, we have this section which is related to this story of chaos, right? And the pole skipping and things like that. But I'm probably, out of 4 offers, I'm probably on the conservative side of this story. So let me not say anything about that. But nonetheless, so you know very well, right? So there are these mysterious connections to of Hydra modes at large values of Q to Lyapunov exponents, to chaos, and these things. So from that perspective, maybe there is a connection of a higher. Maybe there is a story. In fact, the whole distribution of these singularities in the complex Q-squared plane may be of some interest generically, right? So what exactly? I mean, how do they behave in general? So we just looked at very simple. I mean, we computed maybe 2 or 3 of them, right? But it's very easy to see what they do in a complex plane and whether or not they are related to any properties of the underlying QFT, as, for example, this chaos story shows. But we have nothing substantial to say on this at the moment.
Okay, thank you.
Do we have other questions? Anybody? Okay, so okay, good. Well, then I would say we can close the official part of this this session. I thank Andrei again, and like as usual, we will stop the recording, and everybody who would like to stick around a little bit for informal discussions is welcome to do that. Everyone else, thank you for participating, and see you next week.